Hey everyone, Morgan here. So we are going into the world of chemical kinetics now in AP Chem. And it's a new lecture outline called the Kinetics Lecture. We're on page 1. And we're going to start off today by actually talking about some basic definitions. There's two terms that we really need to understand clearly and make sure that we can distinguish between them. So the first is time. And I'm going to somewhat sarcastically say time is what you measure with a watch. Okay? Typically, our unit for time is going to be seconds. Now, rate. A rate is how a quantity changes with respect to time. All right, so what that is saying is something like miles per hour or hamburgers per week. Okay, it's going to have seconds in the denominator rather than in the numerator. Okay? All right. These two words must be understood. We have to be able to tell the difference between them. That is definitely something that's important. Okay, so then what is chemical kinetics? It's the study of the rates and mechanisms of chemical reactions. And I'm going to put a heavy emphasis on mechanisms. And my reasoning is that a lot of people don't. And this is one of those places where if you can get one of these points on the AP exam that somebody else can't, that helps to push you up towards your 5. Okay, and reaction rates. That'll be the change in concentration of a reactant or product per unit of time. Now what that looks like is that reaction rate, capital R, that's our symbol for reaction rate, capital R, by the way the units will be typically molar per second, will equal the change in the concentration of something divided by the change in time. And I'm using kind of a scripty T here because we're going to be having stuff that involves temperature in this chapter also. I'll use a capital T for that. So that equals C2 minus C1 over T2 minus T1, which will look an awful lot like slope for you. Okay, Algebra 1 skills coming back in. So let's use these two examples here that are very popular in kinetic studies because of the presence of NO2. NO2 is a brown gas, so it's easy to measure its concentration using a spectrophotometer. So for that first equation, let's define the rate. Rate equals negative the change in concentration of N2O5 divided by the change in time. Now we have defined the rate that way. That's how we're considering rate, okay, for this reaction. Which means we put the negative sign because N2O5 is a reactant and it gets used up. So the slope for that line would actually be negative, and we don't want a rate that's negative, so we put that minus sign there. Okay? So how does that compare to the rate of production for NO2? It equals 1/2 the change in concentration of NO2 per change in time. Because you see it's a mole ratio. It's 2 to 4 or 1 to 2. Twice as many NO2s form as N2O5s disappear. So to have those rates be equal to each other, that's the important point, it would have to be 1/2 of that. Now this can also equal positive 2 times the change in concentration of O2 per unit of time. Okay? That's all just mole ratios, stoichiometric stuff. Very easy to do in a mathematical question because it's just a mole ratio like we used back when we were doing stoichiometry. Now, let's talk about the second reaction in terms of graphical data. And you might actually remember that you did this as a homework in honors last year. You created this graph. Do concentration. I'm not saying the concentration of what, because I'm going to be talking about different species. First off, I have a line coming down which represents the concentration of NO2. Remember, we're talking about the second reaction now. It is a reactant, so it is going to be consumed. The reaction has its fastest rate in the very beginning when we have the most substance present. Okay? Now, I'm going to draw another line here. Goes up like that. That is going to be the concentration of NO. It's being produced, so positive goes up. And a third line here, trying to make it about half the height of that other one, that's going to be the concentration of O2. It is produced also, but it's produced at a different rate. Not as much of it stoichiometrically, half as much as the two NOs, okay, which means the concentration will be half as much. Okay, there we go. That's page 1 of the outline, and I will tune back in and do another video for page 2 next.